Hello, welcome back. In this video, we'll discuss the acceptance angle and the numerical aperture of an optical fiber. The acceptance angle and the numerical aperture of an optical fiber or any device for that matter are important parameters. The more is the acceptance angle, one is likely to have a higher numerical aperture for the device. It could be an optical fiber. Consider a step index fiber. In a step index fiber, we know that the refractive index across the core is a constant and also across the cladding it is a constant. The refractive index profile looks something similar to this. When the fiber is placed in an environment where the refractive index is N0. Suppose N0 is the refractive index of the surrounding medium. N1 is refractive index of the core. N2 is refractive index of the clad or cladding. From the surrounding medium, a ray is entering into the optical fiber. The ray is touching the axis. It is making an angle theta I. Theta I is the incident angle at the surrounding and core interface. The incident angle at the core surroundings interface. Similarly, after touching the core, the ray would refract into the core. The angle of refraction is theta R. Theta R is the angle of refraction at the core surroundings interface. After the refraction, it propagates through the core and it touches the core cladding interface at this point. At the core cladding interface, the angle of incidence is phi. Phi is the angle of incidence at core cladding interface. Please note that here we are discussing two different interfaces. One interface is between the surrounding medium and the core material, and the other interface is between the core and the cladding. If the incident light after refracting touches the core cladding interface with an angle that is greater than the critical angle of incidence, then total internal reflection would occur. As a result, the incident light will reflect with angle phi that is equal to the angle of incidence at the core cladding interface. Phi is also angle of reflection at core clad interface. In this, we'll assume that the refractive index of the core is higher than the surrounding medium, and also the refractive index of the core is higher than the cladding. So we write N1 is greater than N0 and N1 is greater than N2, where N1 is the refractive index of the core, N2 is the refractive index of the cladding, N0 is the refractive index of the surroundings. Now we shall apply Snell's law at the launching phase of the optical fiber. Applying Snell's law at the launching phase of the fiber gives sin theta I upon sin theta R, which is equal to N1 upon N0. If theta I is increased beyond a limit, phi will drop below critical angle phi c. If theta I is increased beyond a limit, then phi will drop below the critical angle, say phi c. If phi c is not met, then the ray will enter into the cladding. So the largest value for theta I occurs when phi is equal to phi c. Maximum of theta I can be only when phi is equal to phi c. Under such conditions, in triangle ABC, in this triangle, we write sin theta R is equal to sin 90 minus phi, which is equal to cos phi. Say this is 1. And from the Snell's law, we write sin theta I is equal to N1 upon N0 cos phi, because sin theta R is equal to cos phi, and sin theta I max can occur when N1 upon N0 cos phi c. From Snell's law and critical angle of incidence, we know that sin phi c is equal to N2 upon N1, which implies cos phi c is equal to 1 minus sin square phi c to the power half. That is equal to 1 minus N2 upon N1 square whole to the power half. This is equal to n1 square minus n2 square upon n1 square whole power half. This can be written as square root n1 square minus n2 square upon n1. What is this quantity? This quantity is cos phi c. Having written cos phi c, we can write sin theta I max. Sin theta I max is equal to n1 upon n0 into square root n1 square minus n2 square upon n1. So this will be equal to square root n1 square minus n2 square upon n0. Very often, surrounding medium is air. N0 can be taken as 1. So from this we write theta I max is equal to theta 0. This gives sin theta 0 as square root n1 square minus n2 square, or theta 0 is equal to sin inverse n1 square minus n2 square. Here, theta 0 is often called as the acceptance angle, or often it is written as theta A. The acceptance angle is defined as the maximum angle that a light ray can have relative to the axis of the fiber and propagate down the fiber. In this discussion, we are assuming that the incident ray is touching the axis of the optical fiber. Greater is the acceptance angle, more and more light can enter into the optical fiber. From the values of n1 and n2, one can define a quantity called as fractional refractive index change or relative refractive index. The fractional refractive index change is represented with a delta, and it is defined as the difference between the refractive indices of the core and the cladding. The fractional difference delta between the refractive indices of core and cladding is known as fractional refractive index change. Mathematically, it is expressed as delta is equal to n1 minus n2 upon n1. Delta is always greater than 0 or positive because n1 is greater than n2, and delta will always very much less than 1. In the fiber optics, the difference between the refractive indices of the core and the cladding will be very small, and delta will be close to 0.01. Now we shall discuss the numerical aperture. The numerical aperture is a measure for the light gathering ability of the optical fiber. It is a measure for light gathering ability of optical fibers. The light collecting power or the light gathering ability of an optical fiber depends on two factors. One is the numerical aperture and second one is core size, means the core diameter. Mathematically, the numerical aperture is defined as the sine of the acceptance angle. Numerical aperture for short is written as NA, that is equal to sin theta A. And we know that sin theta A is equal to square root n1 square minus n2 square. So numerical aperture is also equal to square root n1 square minus n2 square. One can write n1 square minus n2 square as n1 minus n2 into n1 plus n2. This can be written as n1 plus n2 upon 2 into n1 minus n2 upon n1 into 2n1. Approximating n1 plus n2 upon 2 to n1, one can write n1 square minus n2 square as 2n1 square delta, or one can write the numerical aperture as NA is equal to square root 2n1 square delta, or this is equal to n1 square root 2 delta. If the numerical aperture is more light can enter into the optical fiber. Here we are giving comparison between two optical fibers, one with lower numerical aperture, the other one with high numerical aperture. Here the angle is low, small amount of light can enter into the optical fiber. Here the numerical aperture is large. As a consequence, more light can enter into this optical fiber. In this video, we have started our discussion by considering a step index optical fiber for our discussion. We have said N0 is the refractive index of the surrounding medium, N1 is the refractive index of the core, N2 is the refractive index of the cladding of the optical fiber. We have applied the Snell's law at the launching phase of the fiber, and we have obtained a relationship for the theta I maximum, sin theta I maximum as N1 upon N0 cos phi c, where phi c is the critical angle of incidence for the core cladding interface. From that, we have obtained theta 0 or theta a, which is called as the acceptance angle, as sin inverse square root n1 square minus n2 square, and we have defined the fractional refractive index change delta. We have said delta is equal to n1 minus n2 upon n1. We have stated what numerical aperture is. We have said it is a measure for light gathering ability of optical fibers, and the light gathering power depends on two factors: numerical aperture and pore size of the optical fiber. We have arrived at a value for the numerical aperture using the relative refractive index change. We have obtained the numerical aperture of a step index fiber as n1 square root 2 delta. We have seen the influence of numerical aperture on the light collecting power of optical fibers. Greater is the numerical aperture, more will be the light entering into the optical fiber. Thank you.